We did have one assignment, but that's hardly enough. So the grading mechanism will be this. Each one of you will have to present one topic, one application topic. Okay? So present means present. It does not necessarily have to use slides, but slides will be better perhaps. Be easier for you. Is everybody okay with that?
So what about the topics? Will you suggest some of them so that
I will suggest some of them, but you can also choose your own and suggest them back to me. So that's it. Say one obvious immediate topic that is up for grabs right now is molecular vibrations, and I will just talk about the overall headlines of the topic. That is, I will just tell you what the basic topic is, what to put it in, how much to put it in, and how much detail you want to cover in a class of 1.5 hours, the same as ours, as mine. That's up to you. You should choose yourself. Okay, I will not tell you what to put in and what not to put in, but then I will judge and grade according to how much or how well. If you put in too much and don't get it across properly, that's a demerit. If you put in too little, that's also a demerit. So you have to strike a balance and decide what to put in, what not to put in, how much you would reasonably be able to say, and so on.
Also, sir, at the beginning of the course, you said that you asked us to make notes for each of the classes.
Yeah.
And that would be part of the grading. Is it
Yeah,
still
right.
the plan?
It's still there. It is still there. So
Okay.
that will be one part. This will be the assignment. Maybe I will give you one or two more, but those are hardly very can hardly be very big parts of the grading. The bigger part of the grading will be these two things: the notes you prepare and this one.
So, will these presentations be in regular classes or will be on separate sessions, different sessions?
That depends. That depends on whether we can find extra time. Because frankly, I still need to now. I think I've talked almost enough about finite groups. Although there's one finite group in particular which I need to talk about because that's going to be important for the other part as well. And then we have to talk about continuous groups, in particular Lie groups, and at least some specific things about Lie algebra. So that will take me around at least 6 classes or so. And we don't, in any case, we don't really have to adhere completely to the same end of course guidelines that we have, but it would be good if we could wrap it up, if not by November, at least by the first week of December also.
Also, what will be the duration of each presentation? Like, how long do you want?
That depends. Actually, say roughly 1 hour to 90 minutes. It's a you have to present a full topic. It's not a, so it's going to be a class, not a presentation that way. Okay, you are going to teach the rest of us. Whoever is going up for that day will have to teach the rest of us that particular topic. Okay. So it's not a 20-minute presentation or a 15-minute presentation or something like that. It's a full class. If you feel that you can, yeah, go ahead.
Can I skip it?
Why?
I don't know. It's going to take a lot of time, and I'm really short.
Okay, well, in your case, you can skip it, I guess. But it would be a good idea if you tried it. It will not really take that much time. I'm not going to ask you to do the next one, but then.
Okay.
Think about it.
Okay, so I'll
you don't
think about
have to, but it may be a good exercise to try it. So maybe we will start. Okay, we will give you all one more week to prepare, and the first presentation will be the week after the next one. So one suggestion is molecular vibrations, another would be, say, SU3. That is the Lie algebra and its connection to particle physics. Those are obvious ones. Then one could be crystal field theory. The splitting of spectra in a crystal field. These are just my suggestions. You can come up with other topics. Okay. So today what we were going to do is we are going to end up, I've already told you all the basic theory that you need for finite groups, most of it. I will talk about one finite group today, one specific finite group. So that's because it's the representation theory for that finite group sort of is also used for things like representation theory for SUN and so on. So we will need to learn a bit about this finite group, a bit more than we already have. So let's talk about that. You all might have been able to guess which finite group I'm talking about. I'm talking about SN, the permutation group for n elements. One such permutation group, of course, we have been dealing with. That's S3. But we have really not dealt with S3 as S3. We have dealt with it as isomorphic to the set of symmetries of an equilateral triangle, right? It turned out that the group had 6 elements, and these 6 elements were in one-to-one correspondence with the permutation of the 3 vertices, and so you had this S3 connection. But what we want to talk about is something more general about permutation groups, simply because it's going to be pretty useful in talking about other representations, even representations for continuous groups later. So now, one of the first things that you would learn about S3 is Sn in general is how to represent permutations, and all of you know that. So I'm just sort of writing down, say, one arbitrary permutation that comes to my mind of 8 objects. So this, of course, is a permutation because the lower line is just a rearrangement of the top line, and this, of course, means 1 goes to 2, 2 goes to 3, 3 goes to 1, and so on. And now, I'm pretty sure all of you know this. You can also rewrite this in this form. You start with 1, ask where it goes to, that it goes to 2, then ask where 2 goes to, it goes to 3, and 3, of course, goes back to 1. So you have got a cycle, 1, 2, 3 cycles among themselves. Then you have 4 goes, of course, 1, 2, 3 is taken care of. Then you go to the next one, 4. 4 goes to 5, 5 goes to 7, 7 goes to 6. Okay, 6 goes to 8, and 8 goes back to 4. So this has a 3 cycle and a 5 cycle. So this particular permutation is composed of a 3 cycle and a 5 cycle. Okay, I hope everybody knows that 2 cycles play a very important role in the theory of permutation, right? You know that, I hope. Yes? No?
All cycles can be split up into 2 cycles. Composition.
Yeah. So basically 2 cycles are transpositions, and you can figure out how to do any permutation in terms of 2 cycles. And ultimately, you count, and though the precise number of 2 cycles for a given permutation is not fixed, whether the number of 2 cycles is even or odd, that is fixed, and that decides what the sign of that permutation is. So this symmetrization, anti-symmetrization that we do all the time for identical particles, all that is actually part of this theory. But this cycle structure that we have written down, forget two cycles in particular. In general, any permutation can be written down in a cycle structure. So the question I have for you is, why is the cycle structure so important for permutations? In the light of whatever we have discussed so far about groups, what's so special about the cycle structure? Any idea?
Same cycle structure belong to the same conjugacy classes.
Right. And why is that important for us?
we can characterize the conjugacy classes.
Close. I guess that's what you were trying to. What you were trying to say is not really accurate. I guess you can't characterize the conjugacy classes with irreducible representations, but there's a one-to-one correspondence between conjugacy classes and irreps. So if you have some means of either counting or displaying conjugacy classes, you have a good enough means of sort of talking about irreps of Sn, and via Cayley's theorem, essentially of irreps of all finite groups, and via a slightly more tricky thing, but basically something which ultimately ends up being very simple for a specific group in question, also all irreps of various SUNs. So we will talk about that later. For the time being, let's just establish this one statement that the cycle structure determines the conjugacy class, and for that you have to realize that if you take a permutation pi and take a permutation another permutation sigma and form pi prime, which is sigma pi sigma inverse, that is another permutation conjugate to this permutation, right? That's what it means when they belong to a conjugacy class. So what does pi prime do? It's simple to see that pi prime takes sigma I as an input and produces sigma of pi I, right? Is that okay?
Yes, sir.
Yes, sir.
Good. So pretty straightforward. Okay, let's take this particular permutation. If this is pi, and let's just take some other permutation. Say sigma is 1, 3, 4, 2, 5, 8, 6, 7. Then what happens? What is pi prime? Pi prime essentially, pi is 1, 2, 3. This is the cycle. Then 4, 5, 7, 6, 8. Right? That's another cycle. What pi prime does is it takes sigma 1, where 1 is this one, and gives it to sigma 2, right? Because sigma I goes to sigma pi I. Sigma 1 goes to sigma 2. That goes to sigma 3. And sigma 4 goes to sigma 5. That goes to sigma 7. That goes to sigma 6. That goes to sigma 8. Now, of course, I can now take what sigma 1 is, etc., and I can write this down. Sigma 1 is, of course, 3. Sigma 2, as you can see here, is 5. And sigma 3, as you can see, is 4. So there's a cycle 3, 5, 4. And sigma 4 is 1. Sigma 5 is 8. Sigma 7 is 6. Sigma 6 is 7. And sigma 8 is 2. So that's the permutation pi prime. But it's obvious from this that pi prime and pi must have the same cycle structure. 1 3 cycle, 1 5 cycle. Okay? And conversely, it should be pretty easy to understand that if two permutations have the same cycle structure, doesn't matter what these letters are, but if say you thought of a pi double prime, which is say P71, so 2, 4, 6, 8, 5, then I can obviously cook up a sigma which will take pi and conjugate it to pi double prime. Can anybody suggest what that sigma will be? Let's not call it sigma, let's call it tau. What should that tau be? Oh, by the way, it's not only one tau that will do the job, but can you at least give me one tau that will do the job? That is one tau such that pi double prime is tau pi tau inverse. This is your pi. This is a pi double prime. They have the same. We have already established that if whatever cycle structure pi has, pi sigma inverse must have that same cycle structure, basically because of this situation. But now I am asking you to prove the other, or at least show me that the other way around things also work. That if two permutations are the same cycle
Sorry,
structure,
your presentation stopped.
Oops. Okay, let me just get back my presentation. I'm back. Okay. So I was just saying this, that you have this permutation pi 1, 2, 3, one cycle, and 4, 5, 7, 6, 8 another cycle. Can you show me that you can find a tau such that pi double prime, another permutation with the same cycle structure, is actually conjugate to it? At least give me one example. It should be pretty straightforward. It's not the only possible tau. Tau is not unique, but let me just give you a hint. Let's write down at the top line this in pi. I've not written down 1, 2, 3, 4, 5, 6, 7, 8 in that order. I've just written it out in the order in which you have here. Now can you tell me what tau should be? I hope everybody knows that I can rewrite the top in any order as long as I also rewrite the bottom in that order. And I'm talking the same permutation, right? Everybody knows that, I hope. Because the permutation only says 1 goes to 2 and 2 goes to 3. It doesn't really say that 1 has to be the very first one on top here. It's just a conventional way of writing it. I can use any other order. But can anybody tell me what at least one example of a tau which will work where 1 maps to what? Is the question clear to everybody?
One maps to 3.
Yeah. 2 maps
to 7.
2 maps to 7. Yeah. 3 maps to
1.
Then 4 maps to. Okay,
2.
I guess you've got it. 4 maps to 2. 5 maps to
4, 6, 8, 5.
2, 4, 6, 8, 5. You can just write this down. And then if you want to, you can convert this back to the standard order or write it as cycles or whatever. Right? This will definitely do the job. But now I have a homework for you. At least think about it. How many different taus will do the same job? We are given 3 cycles and a given permutation with a 3 cycle and a 5 cycle. Another given permutation with the same cycle structure. Can you figure out how many different taus will give you pi double prime as tau pi tau inverse? Is this the only possibility?
There should be 15 such possibilities.
Why?
Like instead of 371, we could have 173 and 731, like 3 permutations of the 3 cycles and 5 permutations of the 5 cycles. So 3, 5 is 15.
Right. So in general, this kind of question actually becomes very important because this helps us to decide how many different elements a conjugacy class can have and questions like that. Well, just to follow up on that, can you tell me this? Suppose I have a cycle like this 1, 2, 3, 5, and then you have 6, 7, 4, 8. So that's two cycles, okay, and 1 4 cycle. So how many cycles will be there in this conjugacy class?
The 2 cycles shouldn't have any other configurations as such. Like 2 1 is not possible because it's the same thing.
No,
So 6
okay, 2 1 is not possible because it's the same thing. Fine.
and
Then
5 3 as well. So
yeah, but it
6
doesn't have to 2 1, by the way. It could be, instead of this, you could have 4 8. This is another.
1 2 3 5.
This is another conjugacy, another cycle, another permutation in the same conjugacy class. Of course, 2 1, 5 3, 7 4 8 6 has the same cycle structure, but you should not really count it again. Why? Because you have already counted it. This is the same permutation as this one. Or 3 5 1 2 6 7 4 8. You should not count it again because you already counted that. Right? But this one and this one are distinct ones, right? So that should be a big enough hint as to how to count the number of elements in the conjugacy class. But the number of elements in the conjugacy class is very, very important for figuring out.
Half of 8C2 and 6C2. I mean, it's a guess.
No, let's do it more. Let's do it more systematically. There are 8 numbers here, right? And you can, of course, rearrange them in 8 factorial ways, right? But 8 factorial rearrangements will not all give you the same, give you different classes, different elements in the conjugation class, right? If you keep these brackets in place and just rearrange the numbers, okay, that you can do in 8 factorial ways. Okay. Every time you do that, you're going to get a new, get what looks like a new permutation in the same conjugacy class. Is that okay? However, not all of these new permutations are actually, all of these apparently new permutations are actually new permutations. So to just figure out the fact that this 8 factorial is actually an overcount, because some of these permutations give rise to the same overall, some of these 8 factorial permutations of these numbers will give rise to the same permutation. For example, this one, you have to be able to figure out how many times you're overcounting. So this 1 2 cycle, okay, how many ways can you permute this and yet stay the same?
One more way.
So there are 2 ways, right? 1 2 and 2 1, both of them actually mean the same thing. Okay, so that's a factor 2 overcount. There's a factor 2 overcount here. T5 factor is the same thing. And that goes for all of them. Once you have counted 4 8, you should not count 8 4. Once you have counted 6 7, you should not count 7 6. But in addition to that, there's one more thing. This overall flip, 3 5 1 2, flipping one to the other, that also doesn't give you a way, right? Give you a new thing. So what factor should I put in so that you get rid of that overcount?
2.
Yeah, but this is slightly different. This is actually 2 factorial. It is 2, but if suppose you had 3 2 cycles, then that factor would have been 3 factorial, right? 3 factorial different ways of rearranging the 2 cycles among themselves. And is that all? Is that the entire set of overcounts, or do you have something else?
4 cycle permutations.
So
the rotations.
Yeah, so how many are there?
4.
4. Right. So the number of elements in this conjugacy class is actually quite a lot huger than was proposed a while ago. So if you cancel this out, that's a 7 factorial from which you get rid of, so 2 into 3 into 5 into 6 into 7. 210 into 6, 1260. So there are 1260 elements in the conjugacy class of this. Okay, not a very small number. And that's to be expected. After all, how many elements are there in S8? That's 8 factorial. That's quite a huge number, right? But the important question could be, first of all, can I generalize this formula? Suppose I have in Sn, where n is some fixed integer. Suppose we have k1 1 cycles. 1 cycles, of course, are elements which just don't move on permutation. K2 2 cycles. K3 3 cycles. And so on. So first of all, can you tell me what relationship this K1, K2, K3 must have? Can they be independent? Completely. The number of 1 cycles, number of 2 cycles, number of 3 cycles, etc. First of all, what is the maximum K that maximum I can that you can have here? What's the maximum size of a cycle?
N.
Yeah, right. You can't have any more than an n cycle, of course. An n cycle, of course, is one in which all the n participate. All of them are cyclically permuted somehow or the other. One single cycle. Okay, fine. But if you have, for example, if you have even one n cycle, you can't have anything else, right? You have already exhausted the entire thing. So what is the connection between K1, K2, K3, Kn, etc.? They can't be independent of each other. If Kn is 1, for example, everything else has to be 0.
Sum over I into Ki equal to n.
Yeah, so it's going to be K1 plus 2K2 NKN equals n. Right? That's the obvious connection, simply because this just counts the total number of elements. The number of 1 cycles, if that's K1, there are K1 elements in that. K2 number of 2 cycles takes 2 K2 elements and so on. Overall, you have only n elements. So this is an equation which has to be followed. Now, this is really not that enlightening, but this can be written in a rather nice way, which is, if you count this, and call this, let's say, lambda 1. Then you just take and call this lambda 2 and go all the way down, lambda n, which is just kn. Then you see one thing. This immediately gives me a statement about the lambdas. First of all, what happens when I add all the lambdas?
You get n.
I'm going to get n, right? Because that's just this expression. You get only one K1. 2 of these lambdas have K2 in it, so you get 2 K2 when you add. 3 of these, that is lambda 3, of course, which I didn't write, starts at K3, and so on. So basically, if you add them together, you just get this relationship. But what you also have, so lambda 1, lambda 2, lambda n is just positive integers which add up to n, right? So that, of course, is a much simpler relationship than having n positive integers which has some weighted combination which adds up to n. Here we just have positive integers, or at least non-negative integers which add up to n. And then you have another property, which is lambda 1 must be greater than or equal to lambda 2. right? Because lambda 1 has k1 extra, and k1 is the number of one cycles that can at worst be 0. It can't be negative. So this will all automatically follow. And lambda n is kn, then of course that has to be positive, greater than or equal to 0. So what you have here is a lambdas essentially are positive non-negative integers which add up to n non-negative integers which add up to n. Okay. Now the question, of course, you cannot have more than n non-zero non-negative integers adding up to n anyway, because the smallest value has to be 1, and you can't have more than n such. So now the question for you is this: do you realize that the cycle structure, which essentially counts how many of which cycle you have, okay, and these lambdas, which are just the partitions of the integer n, in how given a positive integer n, in how many ways can you write it as a sum of other positive integers? Do you see that there's a one-to-one connection between k's and lambdas? It's obvious that given the k's, I can find out all the lambdas, right? So for any given set of k's, you have a given set of lambdas. That's right here. That's the explicit formula here. But the other way around it also works, right? K1 is simply lambda 1 minus lambda 2. K2 is simply lambda 2 minus lambda 3. All the way down to the line, Kn is simply lambda n, and there's no lambda n plus 1, so Kn is simply lambda n. Of course, that's just the last equation here. Right? So what does this tell you? It tells you that if you are given a partition of an integer n, then that partitioning of the integer, oops, wanted to put it after. Are you still here or?
Yes, sir.
Okay, good. So is this clear to everybody? Okay. I think this somehow forgotten the meaning of the word after, or maybe I'm in the wrong place. Okay, now I should. Yeah, now it's okay. Now, so what this means, for example, let's just take an example. Let's take S5. How many ways can you partition 5? Well, that's one partition. Another. So 7 possible partitions. Each partition corresponds to one cycle structure, one set of lambdas, and that immediately corresponds to one cycle structure. Okay. So for example, this partition, which essentially is 5 followed by 4 zeros. Right? These are the lambdas. Lambda 1 is 5, all the others are 0. So these are the lambdas. What are the k's? Can anybody tell me that? Yes?
K5 equal to 1.
That's K5 equals 1 or K1 equals 5?
Doesn't the first partition mean there's one per cycle, 5 cycle?
No, that depends on how you decide. If you go by the way I ordered it, this would not mean that. There are, okay, by the way, there are two different conventions which are often used. If I go by the convention that I just introduced, that if you start from the K1, K2, K3, Kn, and now you go to lambda 1, lambda 2, lambda 3, lambda n, and these are the lambdas, these are not the Ks. By the way, this is 5, this is, by the way, if this meant 5 1 cycles, what would this one mean?
1 4 cycle and 1 1 cycle.
Why would it mean 1 4 cycle and 1 1 cycle? Okay, 1 4 cycle, 1 1 cycle. This could be 1 3 cycle, 1 2 cycle. Right? That's one way of looking at it. The other way of looking at it would be these are just the lambda values, which is, by the way, the standard way in which things are represented often. This is 1 5 cycle. Okay. This is not 1 5 cycle. This is basically lambda is 5 0 0 0 0. That means K, which you find by subtracting subsequent values, will be 5 0 0 0 0. That's just, in fact, this is easier to code on a computer. And this actually tells us that this one corresponds to 5 1 cycles, not 1 5 cycles. By the way, these are conjugate descriptions of each other, and you can go from one to the other, but this is better to stick to one. And most books stick to this one. So, for example, this one, 3 2 is 3 2 0 0 0. That's for the lambdas. For the Ks, this would be
1 2 0 0 0.
1 2 0 0 0. And this would mean 1 1 cycle, 2 2 cycles. Okay. Right?
Got it.
And then, so now what you get is, this of course gives you the partitions. Okay, this allows you to tell me how many possible partitions. Each possible partition corresponds to one unique cycle structure, because the Ks tell you what the cycle structure are. But given a lambda, you can uniquely get the K, and vice versa. So there's a 1-to-1 correspondence between the lambdas and the Ks. So given a partition, you can find out a unique cycle structure. That means you can label each class by a partition, or the number of partitions of 5 is simply the number of conjugacy classes. And as for dimension, let's talk about a basic formula. Suppose I have this K1, K2, K3. If you knew these numbers, how many 1 cycles, how many 2 cycles, etc. are there? How many elements are there in the conjugacy class? The answer would be, take n factorial, which is all possible permutations. Then what do you have to do? Then for the ith number here, take, there are ki I cycles, right? And we have seen that every time you have a cycle, there are repetitions in this permutation. There's n factorial permutation of the numbers. They end up giving you the same thing in many ways. So what are the ways? If you have an I cycle, that is, you have I elements in a cycle, first of all, a permutation will not tell you anything, give you anything new. If you could actually just move these things cyclically, right? Is that okay? If you had X, Y, Z, W, and so on, and so that you did Y, Z, W, X, it means exactly the same thing. Although it's a permutation, it means the same cycle, right? So how many such things can you do?
I.
Right. But if there are KI cycles, there's a factor of I overcount for every one of the KI cycles, right? So we have 2 such 4 boxes. There are 4 permutations here which will not change anything. There are 4 permutations here which will not change anything. So it's actually I times I times I, Ki times. So that's I to the Ki. But in addition, if you were to permute these cycles among each other, that will also not change anything. It doesn't matter whether you write a cycle ahead or below, before or after, you get the same result. So in addition, there's a ki factorial. So this is the general formula. You have to take the product of all I from 1 to n and divide by this factor. Is it okay with everybody? Yes? Did you get this, or does this require any further explanation?
No, sir, it's fine.
Okay, great. Now, okay. How many of you have heard of or used Young tableaus? Young diagrams, Young tableaus?
I have not.
Okay, anybody here who has used Young diagrams or Young tableaus?
Even I didn't. So.
Okay, so Young diagrams are important, and especially Young tableaus are going to be very important, especially because they have applications in the representation theory of various groups, especially for the SUMs. For SU2, of course, there are, you know, that there's one irrep for every dimension, but that's really not true for SU3 or SU4 or other higher SU1s. You can have multiple. First of all, you can have multiple irreps for a given dimension. You can also have a situation. You all know that, right? At least SU3, you have done some SU3. Yes or no? Quacks?
Slightly, sir, in the particle physics course last
Yeah, in the
semester.
particle physics course. That's what I'm asking. Have you done something? Then you should know that there are two distinct three-dimensional irreps. And there is
Sir,
no
we didn't look at it from a group theoretic perspective.
But the quacks and the anti-quacks, they are basically irreducible representations of the SU3 group, that way, the flavor SU3 group. Not the SU3 that is there in SU3 cross SU2 cross U1. That's a different group. But when you talk of the particles, the flavor SU3, which essentially is an approximate symmetry because it sort of treats UDS, the three quacks, as identical particles. That, of course, is not really correct. But it sort of gives you a good notion as to why there's a lot of approximate flavor SU3 symmetry that you can see in the world. And the reason why, just to, okay, this is something where I'm getting ahead of the story because we have not done SU3 representations as yet. But basically, the fact that you have triplets of by the way, when Gelman came up with the quack idea, he had no notion of triplets of particles. The quacks, of course, are not observable particles. But he had this notion that there are 8 particles which are nearly identical. You know that, right? The eightfold way. The baryon octet, you have all heard about that, right?
Yes, sir.
There's a baryon octet, there's a meson decuplate, 10 mesons, of which 9 were known, and Gelman actually predicted the 10th, and so on, based on this symmetry theory. But the basic idea is SU3 has an 8-dimensional representation and a 10-dimensional representation. And when I say representation, I mean an irreducible representation. And it does not, for example, have a 4 or 5-dimensional irrep. So basically, the point I'm trying to make is Gelman essentially saw these patterns in the physical world, that you had 8 particles with nearly the same mass, similar behavior, and asked the question, why should there be 8 particles of nearly same mass? And said that, okay, maybe there is some symmetry, which is not an exact symmetry, because then the 8 particles would have been identical, but or states of the same particle, but they are not. But at least they are very close to each other. So he assumed that there has to be some symmetry which is causing this. And then he figured out, okay, the simplest symmetry which has this structure with 8-dimensional irrep and a 10-dimensional irrep, that's the SU3. So that's how he proposed SU3, and then he said, okay, if it's SU3, then the fundamental representation of SU3 has to be somewhere. There must be triplets, and that's how quacks were born. We will come back to this later and talk about this formally. But this is the point is I'm trying to make is representation theory for SU2 is very, very simple. Every dimension has a unique irrep. But for SU3, it's not that simple. Combining SU3s, which will be very important when you ask, okay, I'm pretty sure you've seen equations like this, right? Or 3 cross 3 cross 3. That's of course 27, but you see 10 plus 8 plus 8 plus 1, and so on. I hope you have seen equations like this in your particle physics course. Have you? Yes or no?
Yes, but I didn't understand them. It was more like just looking at
Okay,
it.
so the basic idea is you have a set of three particles which transform among each other according to one representation of the SU3 group. Another set of three particles which transform under another three-dimensional representation of the SU3 group. There are actually two non-equivalent representations of SU3 which are in 3 dimensions. Okay, these are all statements I'm making. We should be able to establish these using the techniques that I'm talking about. But right now we are just making those statements. So there are two distinct three-dimensional representations, inequivalent three-dimensional representations of SU3. One of them, so basically you have three particles which mix among each other when you do a SU3 transformation, which is a transformation in an abstract space. And there, these three particles essentially behave like different states of the same particle. 3 bar, another set of three particles which are basically the anti-particles of these three particles. So the up-down range is 3, up U bar, D bar, S bar are the 3 bar. But if you have a composite system where you take one quark and one anti-quark, and then did a SU3 transformation, what would happen? The quark will transform according to the 3, the anti-quark will transform according to 3 bar, and just like any standard direct product representation, the transformation of the composite system will be this direct product representation of 3 and 3 bar. Is that okay? That is, you have seen this before, right? If you have something like this, and you transform this under LG, what would happen? L alpha G will go and act on V alpha. L beta G will go and act on W beta. And that will give you some okay, I should not really call it V alpha, but let's say Vi and Wj, so dki Vk cross some d beta G Lj Wl. And you have all seen this before, right? You have done this.
Yes, sir.
Okay, so the question is, these quarks transform to a mixture of quark states. The anti-quarks transform to a mixture of anti-quark states. The precise mixture is given by these representation matrices.
So your presentation went off again.
Again? Oops.
Yeah. So why did you remove the alphas and betas from the V and W? Like
no. Actually, the alphas and betas is a bit too restrictive, right? Alpha and beta labels the irrep that you're talking about. Okay.
Yeah.
So what I should have done is actually I could have put in V, but since I was already using V and W, there was no reason to. Since I was using different notations, so I could have said something like this: V alpha, W beta, to show that V transfers according to the irrep alpha, but V alpha I, W beta J.
Okay.
I needed the IJ indices, and since I was already using V and W to different letters, the alpha beta were redundant. I was already showing that they belong to different letters by using different letters. But I couldn't possibly get rid of the actual indices that there are multiple particles there. The important thing is the composite system will transform like the direct product representation, right? But the direct product representation would be reducible in general. And that's something we have already seen in finite groups as well. So a three-dimensional irrep of SU3 and a 3-bar dimensional irrep, which is also 3-dimensional, just another irrep. The bar just shows it's a different representation. The direct product actually has to be 9-dimensional. But this 9-dimensional representation is reducible. It's not an irrep. Okay. And we have already seen this for SU2, right? For SU2, can anybody tell me what this will be? You all know this answer, right? From quantum mechanics. What is 3 cross 3 in SU2? You may not have done this in this language, but you should be able to do it now. Any ideas? Well, 3 here means 3-dimensional representation. In SU2, if you have a 3-dimensional representation, what J are you talking about?
There should be a 5-dimensional one.
Then?
And 1-dimensional.
That would be only 6. Will that work? Well, go back to J's. J's is 1 and 1, right?
And 1 3-dimensional.
So 5 plus 3 plus 1. So that's the rule, which is trivial for SU2. You can, and it's even easier to state in terms of the J's. That's why we often talk in terms of J's and not of dimensionality of representation, right? In SU2, it's very straightforward. But that kind of breakup, that the direct product of 2 3-dimensional spaces break up into 1 5-dimensional, 1 3-dimensional, 1 1-dimensional state. That's something which is true in SU2. In SU3, of course, there's a different group, different representations. You have 2 different 3-dimensional representations. That if you do 3 cross 3 bar, you do not get 5 plus 3 plus 1. You have to figure out what the decomposition is going to be. This is the. I hope everybody understands it when I say 5 plus 3 plus 1 are the irreps for SU2. Is everybody sure? That is for SU2. Can you see the connection between the angular momentum addition rule that we had and this breakup? And why is it that these are really irreps? Is it okay? So when you say J equals 1, what do you really mean? You mean that you have states 1, 1, 1, 0, and 1 minus 1. And when you rotate your coordinate system, these 3 states mix among each other, right? You just get a linear combination of these 3 states. No other states gets mixed up. That's what you mean when you say that these JMs form an invariant space under rotations. And when you say that when you add 2 J equal to 1s together, 1 plus 1, you get 2, 0 or 1. What you really mean is you have 5 states corresponding to J equal to 2, total J equal to 2, which only mix among each other when you rotate. So despite the fact that when you take 3 such states and 3 such states for another particle maybe, that's the J2, you get a total of 9 such states, right? So you have a 9-dimensional vector space which is spanned by these 9 states, 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, minus 1, and so on. Okay? But these are not invariant under, this set of 9 states, or the space of 9 states, space spanned by 9 states, is invariant under rotations, but it's not irreducible. A specific combination of these 9, which you call angular momentum addition, but which really is just finding out which states combine among each other. That specific combination of 5 states essentially span one space. Another specific combination of 3 states span one space. Another specific combination of only one state spans a one-dimensional surface. That is, when you do rotation, that stays itself. Okay, so that's what 3 cross 3 equals 5 plus 3 plus 1 means in SU2. In SU3, of course, the decomposition will be different, and you have to figure out what the decomposition rules are. And for that, the Young diagrams become pretty useful. That's one nice way of doing the decomposition. It turns out that this is a decomposition like this. 3 cross 3, on the other hand, is actually 6 plus 3 bar. And 3 cross 3 cross 3. Sorry. When overboard in the number of crosses, I put a cross a circle around the 3 as well. This is 10 plus 8 plus 8 plus 1. So you have a decuplet, 2 octets, and a singlet. That is the structure of hadrons, things which you make out of 3 quarks. But the point is, how do you know that 3 cross 3 cross 3 is 10 plus 8 plus 8 plus 1? The rule here is not as simple as for SU2. Okay? And one of the easy ways of figuring out this rule is using Young diagrams. Not the only way, but the easy way. Because that's why it's important and interesting to learn about Young diagrams and Young tableaus. Okay, so what exactly is a Young diagram, at least in the context of SUN? Basically, the theory is from SN, and then you adapt it for various SUN. So I'm just going to tell you about the SN part. Hold on, somebody's calling me. Hello? I'm in a class here, check. Okay, so just to go back, 5 was 5, 4 plus 1, and so on. So these are the lambda values. So 5 essentially means 5 1 cycles. So the Young diagram corresponding to that would simply be 5 boxes, one after the other. Or there's another version, I've forgotten what that is called, you just put 5 dots. You would realize that drawing 5 dots is much easier than drawing 5 nice squares. However, the reason why you use squares often is that you want to put numbers in them. This would be 4 squares, the top row, and 1 square in the bottom row. This would be 3 squares, and 2, and so on. So basically, what you are saying is this. Instead of partitioning, or just equivalent to partitioning the integer 5 into 7 of its partitions, you just draw these diagrams where the rule is simple. The rule is, these are the lambda values, right? This is lambda 1 equals 5, and then all the other lambdas are 0, so there are no other rows. This is lambda 1 equals 4, lambda 2 equals 1. So what rule should this diagram obey? If I were to draw diagrams which essentially mimic the same rules for the partitions? Yes? What was the rule for the partitions?
Lambda 1 should be greater than 2.
Lambda greater than or equal to lambda 2, right? So you don't. Why do you have that rule? For the simple reason that if you didn't have that, then you would also talk about 1 plus 4, for example, as another one, and that will not give you a different count. That will be the same count. And of course, the way we define the lambdas, with lambda 1 being k1 to kn summed together, lambda 2 being k2 to kn summed together, and so on, is immediately followed trivially. So when I form all possible Young diagrams, what should the rule be? A diagram like this, for example, would be illegitimate. First of all, if you're talking of S5, this would anyway be illegitimate because you have too many squares. But for S8, for example, you can't have a diagram like this. the number of rows, number of boxes in a row cannot decrease when you go down. Cannot increase when you go down. That's the rule. Is that okay? The number of boxes in each row is the lambda for that row. The number of boxes in the next row can be at best equal to it or less than that. Is that okay? Yes?
Yes, sir. Yeah.
Okay. So if I just use that rule, let me just first write down all the partitions or all the possible diagrams using dots now. This is one of them. I can put 4 dots and then you have only 1 dot left. That's simple. 3 and 2, that's 1. 3, 1 and 1, that's another possibility. Then I have 2, 2 and 1. Then I have 2. And then finally you can have okay. So I've forgotten whose name is attached to these versions where you have dots. When you put squares, you call it a Young diagram, and you call a Young diagram a tableau or a Young tableau, which is what is often used when you put numbers inside the boxes. Okay. Well, that nomenclature is slightly confusing because very often, especially faces, call everything a Young tableau, whether you put numbers inside or not. Okay, but strictly speaking, an unnumbered set of boxes obeying this rule is called a Young diagram. A numbered set is called a Young tableau. Okay, is it okay? You understood the distinction? So what is a possible Young tableau? Say for S8, a possible Young tableau could be something like this. I could have 4 boxes in this row, then you could have 2 boxes and 2 boxes. Let's say that's a legitimate Young diagram. And a tableau would mean I will just put numbers inside, 8 distinct numbers, 1 number to each square. That's the Young tableau. But a special kind of Young tableau is very important, something called a standard Young tableau. And why is that important? Okay, I'm not going into the details of the proofs right now. I'm just giving you the rules. Some of the proofs are pretty complicated, so I will not even give you all the proofs. But let me just remind you why we are so interested in these Young tableaus and so on. Why are we interested in Young diagrams? Because a Young diagram essentially is has the same information as a partitioning of an integer. And why is that of interest to us? Because it tells us about conjugacy classes. Every partitioning tells us about conjugacy classes of a set. But why are we really interested? We are really interested because every possible Young diagram will also have a one-to-one correspondence with an irreducible representation of Sn, right? Because there's a one-to-one correspondence between irreps and classes. There's one irrep for every class, right? So if you can count the number of possible Young diagrams, you already know how many irreps Sn has. Is that okay? Did I get through or so?
Yes, sir.
For S4, for example, let's do it entirely with diagrams. You could have this, that's one possible diagram. Another is this. Another is this. Then you could have this followed by this or this. So 1, 2, 3, 4, 5 possibilities. That means 5 conjugacy classes. It also means 5 irreps. Okay. Now, just like each of these diagrams correspond to a particular partitioning of the integer, hence to a particular cycle structure, hence to a particular conjugacy class, We can also label irrefs with these diagrams. Okay, that's sort of obvious because there are as many diagrams as there are classes. There are as many irrefs as there are classes, hence as many irrefs as there are diagrams. Now, what the Tableau does, what the standard Young Tableau does, is actually it gives us a nice way of representing basis vectors for these permutations, for these irreducible representations. Now, just to point out, if I know here that there are 5 classes, right? So 5 irreps. And S4, how many elements does S4 have?
4 factorial.
So 24. So I need 5 integers. If to figure out the dimensions, I need 5 integers whose squares add up to 24. Okay. Remember, we went through exactly the same exercise when we talked about the symmetric group of a triangle or a symmetric group of a square. There it was pretty easy to figure out 5 integers from this. This one I don't think is that easy, right? Can you find 5 integers whose squares add up to 24?
1, 1, 2, 3, 3.
Good. But is that the only possibility? You should realize that even that is not so obvious, right? It
Yes.
is. You work. This is not too difficult. After all, 24 is still a reasonably small number. But you tried this for S8 or S10. You should see that that becomes very complicated very soon, right? Figuring out all the Young diagrams is not that difficult. But figuring out the dimensions from this simple rule that we had, which was good enough for small groups, is really not going to be that easy for this kind of group, right? Is that okay? So now can I now ask you about one? Okay, let me just, okay, I will not give you the rule, proof of this rule now. Maybe once we start working on this, the proof should be sort of apparent. You can actually treat each of these Young tableaus with numbers in it as vectors and talk of linearly combining them. Now, that may not come. That may come as a surprise if you think of how do you add two tableaus, right? But if you have learned how to add group elements, let's say, you have, right? That gave us the regular representation or the group algebra. You know that given any set of objects, you can just define addition and then go ahead and make a vector space out of it, right? So that shouldn't come as too much of a surprise. My claim is a basis of a representation, of a given representation, a given irreducible representation, which a Young diagram stands for, can be found by using something called the standard Young tableau. And what is a standard Young tableau? The rule is very simple. A standard Young tableau, for example, for this one, the one which I've drawn is not a standard Young tableau. It is a Young tableau, but it's not a standard one. So let me just tell you what the rule is. The rule essentially is this. In a standard Young tableau, every row and every column has to obey this rule, that if you go across a row, numbers has to increase, and when you go down a column, again numbers have to increase. So you see, this is not standard because, okay, this is anyway wrong because this should have been a 6. You have 8 different numbers to put in. But you can see that this is not standard because 1, 7, then you have a 6. You have a wrong order. Okay. This is a Young tableau, but not a standard Young tableau. But this would be 1, 2, 4, 8. Okay. No, sorry. Oops. What happened? This is a standard Young tableau, right? Notice that for every row, it's increasing along the row and increasing along the column. Okay? Clear? So can anybody tell me, okay, let me just try figuring out for this kind of structure for how many possible young tableaus can you draw? The number can be pretty high, but notice that this corner has to be a 1. Is that okay with everybody? Okay, maybe I'm being a bit too ambitious and trying to write down a too big a thing. Let's try with a smaller one. Let's say for S4, are you still with me?
Yes.
Yeah. So you want to write a standard young tableau. That means you put the numbers 1, 2, 3, and 4 in the 4 boxes, obeying that rule. And how many different ways can I do it? Realize that you have to put a 1 in this corner, right? You can't put the 1 anywhere else. Is that obvious?
Yes.
Now what about 2? Where can you put the 2? Well, you can put the 2 here, right?
Yeah.
But you can also put the 2 here. So there's another possible standard young tableau where you have a 1 here and a 2 here. That's also going to work, right? Where do you put the 3? In this tableau, there's only one choice. You have to put the 3 here. You can't put the 3 here because then the 4 will go here and screw up things, right? And that means you have to have 4. But in this case, you have 2 choices. You could put a 3 here and a 4 here. Or you could put a 4 here and 3 here, right? So here you can see clearly that there are 3 possible standard young tableaus that you can write down with shaped with a lambda of 3, 1. Is this clear?
Yes, sir.
Now, of course, given a particular young diagram, you can keep on filling up according to these rules and try to figure out all the possibilities and find out how many possible standard young tableaus you can write down. And as will be clear when we talk about how this basis is actually created, that's for later, you will find that each of these standard young tableaus, essentially, this young diagram, this 3 and 1, that represents an irreducible representation of S4. Okay. And these young tableaus, the standard young tableaus, that gives you the basis vectors, one realization of the basis vectors for that particular irrep. That means that this particular irrep that we are seeing here must be 3-dimensional because it has 3 basis vectors, right? So this gives us a way of keeping track of how many irreps you can have. How many irreps you can have? That's of course how many diagrams you can have. And how many standard young tableaus you can have for a given diagram. That keeps track of what is the dimensionality of the irrep. Okay. So this irrep is 3-dimensional. Can you figure out the dimensionality of this irrep? Again, 1 has to go here. 2 choices for the 2, but if 2 goes here, 3, 4 gets fixed, right? If you put 1 here and a 2 here, then again 3, 4 gets fixed, right? So you have only 2. So this is a 2-dimensional irrep. This is a 3D irrep, the 2D irrep. Can anybody tell me what is the dimension of this? 1 has to go to this corner. Is everybody hopefully is clear about that? The 2 choices for the 2.
It's the same as the previous one.
Same as this one. In that, it's easy to see that this has to be the same as the previous one. This one, 3, 1 and 2, 1 square, which is 2, 1, 1. These are called transpose or conjugate representations. And you have to see that there's a one-to-one correspondence between this and the reflected versions of this, right? You would just transpose the numbers. If the rule is obeyed for, the rule is the same for rows and columns, right? So if you interchange the rows and columns, you should get the same kind of behavior. Okay, so this is also 3D. So this apparently looks like a very simple rule to use, but let's say if I have a diagram like this. So this, of course, will represent an arep of S12. I hope I've counted it right. Yeah. There's one arep of S12, and the dimension of that will be the number of standard Young tableaus possible for this. Now, it's possible to find out all possibilities just by writing things down one after the other. But that becomes too much of work. And you should realize that even if you can do it for this, for a larger Young diagram, that will become very, very difficult to do. Okay. But now I will tell you a rule which will tell you the dimension pretty easily. Okay. And this rule is an important rule and a rather funny kind of rule. Okay, let me just give you a proof of this first. Okay, how many Young tableaus can you create out of a diagram like this? How many Young tableaus, not standard Young tableaus, how many Young tableaus can you create? Given that for this particular Young diagram.
12 factorial, right?
12 factorial, right, of course. And just rearrange all the numbers among themselves. Okay. Now, this number, for example, the number in this corner, what does this have to be?
1.
1. But the basic point is it has to be the smallest possible number among all of these, right? If you consider this thing, this has to be the smallest number in this, right?
Yes.
And how many elements are here? 1, 2, 3, 4, 5, 6, 7, 8, right? Now this is called a hook, and this particular point has a hook number of 8. So you pick any box of your diagram and start from the bottom, go to that box and then turn until you go out of the diagram. Count the number of boxes you encounter. That's called the hook length for that particular point. Okay? Right? Is everybody with me so far? So let me just draw this a bit better. Maybe I will just use lines. Okay, maybe, okay, I've overdrawn things, but that's. So this is a Young diagram I had, and for every point, I can easily calculate the hook length or hook number for that point. Say for this cell, I will just go from the bottom all the way up until I hit this, then turn right until I go out and count the number of cells in the way. So if I do that, I can put the hook number of every point. For example, this point would have a hook number 1, 2, 3, 4, 5, 6, 7, 8. So 8. The hook number for this point will be 1, 2, 3, 4, 5. For this point will be 1, 2, 3. For this will be 2. Right? Is that okay?
So it's not just like L shaped that are nested within each other. So for every cell we have.
For every single cell you find out the hook number.
Okay.
4, 5, 6. So this one, for example, 4, 7. This will be 7. This will be 1, 2, 3, 4. This will be just 2 because you just go up and out. This will be 1, 1. This will be 1, 2, 3, 4. Be 2. This will be 1. It's easy to see the corner points will have 1, but the structure is like this. Okay. Now let me give you an argument using combinatorics. If you were to just think of this hook, what is the probability that how many elements, how many numbers do you have in this hook? 8, right? And this number has the smallest, has to be the smallest among them, right? This corner element has to be the smallest in its hook, right? Everybody with me so far? So what is the probability that if you just took 8 numbers, 8 because the hook length is 8, and you put 8 numbers at random in these 8 boxes, what is the probability that the smallest one will land in that particular corner? So if you just took 8 numbers and threw them in random in these 8 boxes,
1 by 8.
what is the 1 by 8, right? The probability that the smallest one will, there's only one unique smallest one among these 8 distinct numbers, that it will land up in that corner is of course 1 by 8. Similarly, if you looked at this hook which has 7 boxes, and I repeated the same argument, the probability will be 1 by 7, 1 by 4, 1 by 2, so the rule becomes simple. Of course, there are also 3 times 1s here for the 3 boxes with hook length. So this is the rule. The rule is take n factorial, divide that by the product of the hook lengths, and you will get the number of standard Young tableaus, which in turn is the number of the basis vectors for that particular irrep. So anybody has anything to say about this proof? Yes? Any objections or anything? No objections.
Sir,
Yeah.
could you explain the reason why this is so? This
I
case
gave you the
here.
reason, right? I told you that all you have to do is figure out there are 12 factorial ways of randomly populating the Young diagram by putting just 12 numbers.
No, the Young diagrams and
And the standard Young tableaus are ones in which at the corner of every hook, the smallest of that hook has to be. What happened? You're not convinced with that?
no, like you said, the number of Young diagrams possible gives the number of irreps, right?
Number of
And then
standard
the
Young tableaus. No, nomenclature.
No,
Number of Young
Young
diagrams
diagrams
gives you the number of
irreps.
irreps.
Yeah, and
For a given
the
Young
number of
diagram,
standard for given the Young diagram, the number of standard Young tableaus gives the dimension of that irrep.
right?
Why is that part so? The latter part, like.
No, I didn't explain that to you. I will explain that to you when I talk about how the representations are built up. For that, we'll have to cover some more ground. I'm just giving you the result just to for 2 reasons. One is that it's a bit more complicated to show why that is true. And moreover, that is important actually. You will need why that is true when you want to build up various quark states. For example, you think of how to build up, say, hadron states using quarks. You may have already done this in particle physics, may or may not have. But the calculation actually, but the rule there might be a bit ad hoc. You do it for one particular combination, then you try something else for another combination, and so on. But the rule that I'm going to talk about, the rule which involves finding out the irreducible representations from the Young diagrams, that sort of is universal. That works everywhere. Okay. So that's a nice rule to know. The only problem is the rule is complicated to state, and I will take that slowly and explain it later. I've just made a statement right now that each Young tableau, each standard Young tableau, essentially works as a basis. That's the rule which I'm just stated for the time being. Okay, I've not proved it.
Okay.
And I'm not going to prove it now. Hopefully, by the time we end this semester, you will also know the proof of that. Or to put it more truthfully, hopefully by the end of the semester, I will have figured out a way to explain this in a simple enough language. Or just to sort of paraphrase Feynman, that would mean that I understand the proof well enough. I understand the proof, but right now, the version which I know seems to be way too complicated to just say out loud to people. But I have a feeling that the proof can be, at least my understanding of the proof can be simplified enough so that I can explain it to you.
Sir,
Yeah.
we could split up any permutations into cycles, and that's why we could use Young tables and all that. But how would you use it for SU2 or SU3?
Yeah, that we will explain. The connection between SUN and SN. Why is it basically you will find out that the irreps of SUN actually have certain symmetry properties, which you already know, by the way, right? For SU2, you know that, right? You know that if you take two spin halves, for example, which are two-dimensional representations, you combine them together, you get a completely symmetric state and a completely antisymmetric combination, right? You know that. The completely symmetric ones are the triplet, which is the spin one, and the completely antisymmetric one is the singlet. So it's basically this kind of combination. There is an interplay between the symmetrization and anti-symmetrization which SN imposes and the representations of SUN. We are going to explore that. That's pretty. It's actually not just complete symmetrization and complete anti-symmetrization. There are many mixed symmetry possibilities, and these are important things to explore. We are going to talk about that. Right now, I'm just stating this. Right now, by the way, I'm not talking about SUN at all right now. I just mentioned SUN just to sort of advertise that the reason why we need to learn Young diagrams is that if you are a particle physicist and you want to figure out what happens when you combine particles together, when fundamental particles get together, what kind of possible combinations you can get, you need to know how to form direct product representations for different SUNs and then reduce them. And for that job, Young tableaus do a remarkably good job. The reason for that is that there's a connection between permutation symmetries and these representations. So despite the fact that that group is different from SN, it just show up there. But we have not explained why. And right now I'm not talking of this dimensionality for the time being. By the way, it's not the SUN dimensionality. This is the SN dimensionality. I'm talking of SN S12 in particular. And I'm asking what is the dimensionality of the irrep which this diagram shows you. And the answer for that is, the formula is basically n factorial by this. You find the hook length for every box, divide by the hook length, product of the hook lengths. Okay. Pretty simple formula. Final formula is pretty simple, right? But do you have any objection to the proof I gave you? Remember, I'm not even trying to explain why this is the basis of an irrep. I'm just saying, okay, given a standard, how do I find standard Young tableaus? How many standard Young tableaus? That standard Young tableaus correspond to a basis of an irreducible representation is a different level question that we'll come to later. Right now, the question is, how do you find out the number of standard Young tableaus? Which, by the way, is an important question beyond group theory, is an important question in combinatorics. Young tableaus are used in combinatorics all the time. So, without any reference to group theory. And there, the question would be simply a question of, in how many ways can I do this? I don't care whether they stand for a basis or something. The proof I gave you is simply this. I said, in this hook, the probability that the smallest is in this corner is 1/4. For this hook, the smallest is in this corner is half. For this, the probability that the smallest in this corner is 1/3, and so on. And if you multiply the total number of possible, possible permutations, possible young tableaus of this particular shape, or this particular young diagram, by the total probabilities of each of them having the smallest in each corner, or corner of each hook, that is, then you will get the number of standard young tableaus. Can you see why this is a bit iffy, this proof? When do you multiply probabilities?
When you want all the events to occur simultaneously.
No, not really. You throw one coin, one dice, and you get 1. The next time you throw it, you get 2. You do multiply the probabilities, right? They don't occur simultaneously. What do you mean by simultaneously?
I mean, probability of both the events to happen.
The probability of it raining tomorrow is say 20%. Probability of there being thunderstorm tomorrow is say 10%. Would you multiply the probabilities to see whether both occur?
No, they are not independent events.
Right. So the independence is important, right?
Yes, sir.
Simultaneity, you want both of them to happen. Okay, I guess that's what you meant when you said simultaneous. You want both of them to happen, but they have to be independent of each other.
Yes.
But this is no way independent, right? If you say if you take one hook and say that the one which is sitting in the corner is the smallest, that immediately influences the probabilities that for the other hooks which share some legs or arms with it, have the smallest one, and that's their smallest one in that corner, right? They're saying that this hook, for example, for this, the smallest one is sitting in this corner, that immediately influences the probability of this hook having its smallest one sitting in this corner. They're not independent situations anyway. All these hooks have overlaps, and there's no way you can think of these probabilities as independent. So, one funny thing is, this result is perfectly right. The argument is rubbish. It's completely wrong. And it's not the right argument, by the way. No self-respecting mathematician will give you this argument, except that this argument is very nice to remember the result by. It's sort of has a plausibility ring to it. It's total nonsense. The argument is wrong. The result is correct. It's also rather difficult to prove. There are combinatorial arguments, probability-based arguments, which can help you calculate this result, but those arguments are pretty complicated. Okay, but just so happens the final result comes out to be right, even if you make this argument.
So it's like a mnemonic.
So it could be a nice mnemonic. You could of course say, I just memorize hook lengths. That's enough. I don't even need this rubbish argument to sort of help me remember that. But in case you've forgotten hook lengths, remember this argument. It's a pretty straightforward result, and the result is straightforward to use. And the result is not wrong, by the way. This result is correct. It's just that the argument I gave for this result is complete nonsense. So now that you have it, you can easily find out hook lengths and dimensions for each of these irreps. Once again, let me stress, these are the irreps of Sn that we are talking about, for which this rule applies. It will not come as a surprise that for SUN, Young diagrams again play a role, And there also you have a rule like this which will tell you what the dimension is for each Young diagram. And you can have a nice diagrammatic way of joining these Young boxes together and forming the entire structure. Okay, that is, say this result that we talked about, 3 cross 3 bar. We can actually get this by following some standard rules of putting different irefs together, or to be more precise, different Young diagrams for the irefs together, and that will immediately tell me what possibilities you can have and what dimensions will be. So this composition rule, or what kind of representations you can get, and it gets better. You can actually do. You can not only get this, of course, just gives you the reduction, but just like for the orthogonality theorem just gave us a reduction. And it told me how many times a given irrep was occurring in a representation. But it also gave me via the projection operators a means of finding out the basis vectors for that reduction, right? The same can be done using Young diagrams. So that's actually quite, well, it's an important tool for the simple reason that the calculation tends to get out of hand pretty quickly if you start doing it without any other help. The Young diagrams help to keep it organized and do it neatly. So we will talk about Young diagrams in SUN, but that will be after we talk about Lie groups and come to SUN proper. Okay, so next day we'll start with continuous groups and Lie groups. But before we end, I want to have a volunteer for the molecular vibrations presentation. That will be not next week, the week after that. Anybody who volunteers, and I'm still recording so that I can keep a track of that.
So there are only 3 people of the 6 people in this class now.
Yeah, I know. I can see that too. So you mean that's unfair because the other 3 won't get a chance to volunteer?
Kind of.
Or you really meant that? You meant that it's unfair on them?
I mean, it could be that they might be willing, so we don't know their chance. So.
Okay, so that's another roundabout way of saying that you are not willing, right?
Yes, sir.
ठीक है. If nobody volunteers by the next day, which is Tuesday, spread the word. If nobody volunteers by next Tuesday, I will pick somebody by doing
Yes.
eeny, meeny, miny, mo, or whatever.
Yes, sir.
So, I mean, does someone have to present on molecular vibrations? Like, I mean, you said we can choose our own examples too, right? We can.
Yeah, so come up with okay, either do that or come up with your own choice. Each one will come up with a decent own choice by next Tuesday. That's fine.
So in that case, can I do the topic on SU3 group and its application into particle physics?
You can, of course, unless somebody else wants to fight you for it.
Okay, sir.
But you really meant SU3 Lie algebra, right? Not really SU3 group so much.
Yes, sir.
Okay, anyway. But remember one thing, whatever you choose is your baby, you choose it, you do it in your own way. But I will grade you or I will judge you for that particular thing depending on how much you have been able to get across. That doesn't necessarily mean how much material, but how well. It's both how much material and how well. If you just decide to pick up one small thing and spend an hour explaining it very, very well, that's not good. But you explain a lot of stuff without explaining it properly, that's even worse. Okay. This is going to be a perfectly subjective judgment. I am making absolutely no pretense of being able to objectively judge how good somebody's presentation is. But I have a gut feeling as to whether something is good or bad. I'm going to just use that. Okay. So let me call it a day today. Next day, we are going to start talking about Lie algebras. Not Lie algebras, continuous groups, Lie groups. And we will not spend too much time in Lie groups simply because Lie algebras are going to be more useful for us. So we'll quickly transition to Lie algebras. Okay. Right. So I'm stopping recording now that the incriminating evidence has been recorded.